Okay, let's get into it. Number 10. Mars methane. There's a rover on Mars right now, and it keeps smelling something it can't explain. The rover is Curiosity. It's been rolling around the floor of a place called Gale Crater since 2012, and bolted inside it is an instrument that can taste the Martian air with astonishing precision. It fires a laser through a small chamber of gas and reads what's there down to fractions of a part per billion. And over, that instrument has found the same strange thing. Methane. Now, here's why that one word makes people sit up. On Earth, if you find methane in the air, the overwhelming odds are that something living made it. Cows make it. Swamps make it. Microbes buried in rock and mud make it quietly, in the dark, by the trillions. Methane isn't proof of life, but it's the kind of gas that, on our planet, almost always has a heartbeat behind it somewhere. And Mars is supposed to be dead. Cold, dry, blasted with radiation, a planet that lost its magnetic field and most of its atmosphere billions of years ago. There shouldn't be much methane there at all, because sunlight breaks it apart over a few centuries. Any methane you find is, by definition, fresh. Something is topping it up. The background level Curiosity measures is tiny, about 0.4 parts per billion. That's nothing. That's a whisper. But it's not silent, and it doesn't sit still. It rises and falls with the Martian seasons, climbing to roughly 3 times higher in the local summer than in winter. And then, on top of that gentle seasonal breathing, come the spikes. Sudden surges where the methane jumps to 40 times the usual level, and then, just as quickly, fades away. Here's the part that genuinely unsettles the scientists. The methane seems to show up at night and disappear during the day. And when Europe sent an orbiter, the Trace Gas Orbiter, specifically to hunt for this methane from high above, it often couldn't find any at all. So you've got a rover on the ground smelling it, and a spacecraft overhead saying there's nothing there. Both can't be simply right. Something is either destroying the gas incredibly fast near the surface, or it's leaking out locally, right around where the rover happens to be sitting. The official, careful answer is chemistry. There's a process called serpentinization, where water reacts with certain iron-rich rocks and produces methane with no life involved whatsoever. It's real, it happens on Earth, and it's probably the safest bet. But here's the thing. Nobody has actually caught that process happening on Mars. Nobody has found the source. We have a gas that behaves like it's being made and unmade by something we don't understand, on a schedule we can't predict, on a world we were told was lifeless. A robot the size of a car keeps catching the scent of the one gas that, back home, usually means you're not alone, and it can't tell us where it's coming from. Number 9. Glycine on a comet. In 2014, a spacecraft did something that sounds impossible. It caught up with a comet, flew alongside it for 2 years, and rode with it as it swung around the sun. The spacecraft was Rosetta, built by the European Space Agency, and the comet had a name that only a scientist could love. 67P, Churyumov-Gerasimenko. A lumpy, dark, 2-lobed chunk of ice and dust shaped a bit like a rubber duck, tumbling through space. And as that comet warmed up near the sun, it did what comets do. It started to breathe out a thin cloud of gas and dust, a halo called the coma. Rosetta flew straight through that cloud, again and again, sampling it with an instrument that could identify individual molecules. And in that cloud, it found glycine. Glycine is an amino acid. It's the simplest one, but it's still one of the 20 amino acids that every living thing on Earth uses to build proteins. Proteins are the machinery of life. Enzymes, muscle, hair, the tiny molecular robots inside every cell. And here was one of the letters of that alphabet, drifting off a comet, hundreds of millions of kilometers from Earth. That detection came in 2016 from a team led by a scientist named Catherine Altweg. and she was careful about her words, because scientists have been burned before by claims of amino acids in space that turned out to be earthly contamination sneaking into the sample. But this was different. Rosetta wasn't scraping a meteorite in a lab where human fingerprints get everywhere. It was sampling raw gas, directly, out in the vacuum. There was no contamination to worry about. As Altweg put it, this was the first unambiguous detection of glycine at a comet. But glycine wasn't even the most important thing they found. Riding in that same cloud was phosphorus. And phosphorus is the quiet hero of this whole story. It's in the backbone of your DNA. It's in the membranes that hold your cells together. It's in the molecule your body uses to carry energy around. Life, as we know it, simply cannot be built without it. And it's one of the hardest life-essential elements to deliver to a young planet, because it tends to get locked up in rocks. So finding phosphorus and an amino acid together on the same comet is like finding two of the rarest pieces of a starter kit sitting side by side. Now, one amino acid and a sprinkle of phosphorus is a long, long way from a living thing. Nobody is saying that comet was alive, but think about what comets do. They wander the solar system for billions of years, and every so often, one slams into a planet. Early Earth was pelted by them. And here we have direct proof that comets carry the ingredients of life, ready to be dumped by the ton onto any young world that happens to be in the way. The building blocks aren't waiting to be made. They're already out there, already assembled, already flying. And every comet is a delivery truck. Number 8. The Murchison Meteorite. On a September morning in 1969, the people of a small town in Australia called Murchison watched a fireball streak across the sky, heard a bang, and then found pieces of a rock scattered across their fields and rooftops. It smelled faintly of methylated spirits. They picked up the fragments, some of them, and handed them to scientists. That rock turned out to be one of the most important objects ever to fall out of the sky. Murchison is a type of meteorite called a carbonaceous chondrite. It's a leftover from the birth of the solar system, 4.5 billion years old, older than the Earth itself. And when scientists started analyzing it, they found it was absolutely loaded with organic chemistry, not just a trace, a treasure vault. Over the decades, researchers have identified more than 90 different amino acids in the Murchison meteorite. Let that sink in. Life on Earth uses about 20 amino acids. This single rock contains more than 90, and most of them are amino acids that Earth life doesn't use at all. That last detail is the one that matters most, and here's why. If you found only the amino acids that our biology uses, you'd have to worry that the rock got contaminated when it landed in a field full of Australian bacteria. But it's stuffed with exotic amino acids that no living thing on Earth bothers with. That's a fingerprint. It tells you this chemistry was forged out in space, in the cold and the dark, long before it ever reached the ground. It's genuinely, provably alien in origin. And the story didn't end in the 1960s. For decades, scientists tried to find the nucleobases in meteorites. The nucleobases are the other alphabet. They're the letters of DNA and RNA, the code that stores genetic information. There are 5 of them, and researchers had managed to find 3 of them in various meteorites over the years. But 2 of them, cytosine and thymine, stubbornly refused to show up. They're fragile, and the old methods for extracting them used hot, harsh acids that may have been destroying the very molecules they were hunting for. Then, in 2022, a team led by a scientist named Yasuhiro Oba tried something gentler. Instead of hot acid, they used cool water, a delicate touch, treating the rock like it was made of glass. And there they were, cytosine, thymine, the last 2 missing letters. For the first time, the complete set of nucleobases used by life had been found in material from space. So, put it together. A rock older than our planet, carrying the full protein alphabet and the full genetic alphabet. Some of it informs our own biology never adopted. As Oba said, we now have evidence that the complete set of building blocks used by life today could have been sitting on the early Earth, delivered from above, when life was just getting started. The recipe didn't have to be invented here. It fell out of the sky, already written. Number 7. The Bennu Sample. Everything we just talked about, the meteorites, has one nagging weakness. They fall to Earth, they sit in a field, they get handled, and no matter how careful you are, there's always someone in the room asking, "Are you sure that didn't come from here?" So NASA decided to remove that doubt entirely. They went and got a sample from space, sealed it, and flew it home without ever letting it touch our world. The mission was called OSIRIS-REx. The target was an asteroid named Bennu, a dark little pile of rubble about half a kilometer across. The spacecraft spent 2 years mapping it, then reached out with an arm, tapped the surface, and caught a puff of material blasted up from Bennu's surface. It stored that sample in a sealed capsule, turned around, flew back across the solar system, and in September of 2023, dropped the capsule into the Utah desert under a parachute. Pristine, untouched, a piece of an asteroid delivered clean. Then they opened it. And in January of 2025, a team led by scientists named Daniel Glavin and Jason Dworkin at NASA's Goddard Space Flight Center told the world what was inside. Thousands of organic compounds. 14 of the 20 amino acids that life on Earth uses to build proteins. And there were hints of a 15th, tryptophan, which had never been seen before in extraterrestrial material. But it didn't stop at amino acids. They found all 5 of the nucleobases: adenine, guanine, cytosine, thymine, uracil. The complete genetic alphabet. Again, this time in an asteroid sample that had never been near a human until the moment they cracked the seal. And then there was the ammonia. Bennu's sample held about 230 parts per million of ammonia. That's roughly 100 times more concentrated than the ammonia in ordinary Earth soil. Now, ammonia might sound like a boring cleaning product, but in this context, it's electric. Because ammonia can react with formaldehyde, which they also found in the sample, to build more complex molecules, including amino acids. In other words, this wasn't just a bag of ingredients. It was a bag of ingredients plus a chemistry set that knows how to combine them. This is the cleanest evidence on this entire list. No field, no contamination, no handshake with Earth. A sealed sample from a rock in deep space. And inside it, the amino acids, the genetic letters, and the reactive chemistry that leads toward life. Here's the honest part, though, and it's the same honest part every time. Building blocks are not a building. Ingredients are not a meal. Finding the alphabet doesn't mean anyone ever wrote a book. What Bennu proves is that the ingredients of life are scattered across the solar system, common as dust, sitting inside ordinary asteroids by the thousands, which raises a question that's hard to shake. If the ingredients are everywhere and the chemistry to combine them is everywhere, then how many times, on how many worlds, did something actually start mixing them together? Number 6. Enceladus. Saturn has a small moon named Enceladus. It's only about 500 kilometers across. You could drive across it in a day if it weren't a frozen ball at the far edge of the solar system. From a distance, it looks like a smooth, bright snowball, one of the whitest, most reflective objects in the entire solar system. Utterly boring, you'd think. A dead little ice cube. And then the Cassini spacecraft flew close, looked at the South Pole, and saw jets. Enceladus has cracks near its south pole that scientists nicknamed the tiger stripes. And out of those cracks, this tiny moon is firing enormous plumes of water into space. Geysers. It's spraying its insides out into the dark, continuously, in fountains that reach hundreds of kilometers high. And that water is coming from a global ocean of liquid salt water, hidden beneath the ice. Now, a hidden ocean is exciting on its own. But Cassini did something extraordinary. In October of 2015, it didn't just photograph the plume, it flew straight through it. It let the spray of an alien ocean pass directly through its instruments, and it read the chemistry on the way. And what it found changed everything. In the plume, Cassini detected molecular hydrogen. A team led by a scientist named Hunter Waite worked out what that meant and published it in 2017. The most plausible source of that hydrogen is hot water reacting with rock at the bottom of the ocean. Hydrothermal vents. On Earth, hydrothermal vents are cracks in the deep sea floor where superheated, mineral-rich water pours out, and they are absolutely teeming with life. In fact, many scientists think life on Earth may have started at vents exactly like these. And then, in 2018, the team found something more. Large, complex organic molecules, riding in the ice grains of the plume. Not just simple carbon compounds. Big, rich, organic chemistry. So count what Enceladus has, all at once. Liquid water. Check. A source of chemical energy from those hydrothermal vents. Check. And complex organic molecules. Check. That is the exact trio scientists believe you need to start life. Water, energy, and organic chemistry. Enceladus has all three, right now, today. It is, in the words of the researchers, the only body besides Earth known to satisfy all the basic requirements for life as we know it, simultaneously. And here's the beautiful, almost absurd part. This moon is spraying its ocean into space. For free. We don't have to land. We don't have to drill through miles of ice. A future spacecraft could simply fly through the plume, catch the spray, and analyze whatever's in it. If there are microbes in that ocean, some of them are getting flung into orbit right now, waiting for someone to come and catch them. A frozen little snowball at the edge of the solar system, holding a warm, dark sea with hot vents on its floor, blowing samples of itself out into the night. And so far, nobody has gone back to taste them. Number 5. Europa's hidden ocean. Now travel inward, to Jupiter, and to a moon called Europa. If Enceladus is a snowball, Europa is a cracked marble. A smooth ball of ice, laced all over with reddish-brown streaks, like the shell of an egg that's been dropped and glued back together. Those cracks are a clue, because under that shell of ice, Europa hides an ocean, not a small one. A global ocean of liquid salt water, wrapped around the entire moon, and it's estimated to hold about twice as much water as all of Earth's oceans combined. Every sea, every ocean, every drop on our whole planet. Europa has double that, sealed under the ice. How do you keep an ocean liquid that far from the sun? Out where sunlight is feeble and the surface is around minus 160 degrees. Jupiter does it. Europa is caught in a gravitational tug-of-war with the giant planet and its other big moons. And that constant flexing needs Europa's interior like a stress ball, generating heat from friction deep inside. That heat keeps the ocean, perhaps 100 kilometers deep, from freezing solid. For a long time, the ocean was an inference. We could see the cracks. We could measure the way Europa disturbs Jupiter's magnetic field, and everything pointed to a sea under the ice. But it was hidden, sealed, out of reach. And then telescopes started catching something, venting off the surface. Back in 2014, a scientist named Lawrence Roth and his colleagues reported signs of a plume, a spray of water vapor near Europa's south pole, using the Hubble Space Telescope. In 2016, Hubble caught more evidence of the same thing, faint fingers of vapor rising off the moon and falling back down. Not the roaring geysers of Enceladus, but something. Little leaks, hinting that the buried ocean is finding its way to the surface. And that changes the entire game. Because if Europa is venting, even a little, then we don't necessarily have to drill through an unknown thickness of ice to reach the water. A spacecraft could fly through a plume and sample the ocean directly, the same trick Enceladus offers. That's a huge part of why NASA built a mission called Europa Clipper, now on its way to the Jupiter system, to study this moon up close and figure out just how habitable that hidden sea really is. Here's what I keep coming back to, though. We have a moon with twice the water of Earth, kept warm and liquid for billions of years, sealed under a crust of ice, with chemistry we've barely begun to sample. Billions of years is a long time. It's roughly the same span of time that took Earth from lifeless rock to a planet crawling with living things. We have never looked inside that ocean. It has been sitting there, dark and warm and undisturbed, for almost the entire history of the solar system, and we genuinely do not know what, if anything, has been swimming in it the whole time. Number 4. Arsenic Life. Everything so far has been about finding life somewhere else. This one's different. This one is about finding life that's built wrong, and it's a story about how badly we want the answer to be yes. In 2010, NASA called a press conference, and the buzz beforehand was electric, because the agency had teased that it was going to discuss a finding that would impact the search for extraterrestrial life. People genuinely wondered if they were about to announce aliens. What they announced instead was, in some ways, even stranger. A scientist named Felisa Wolf-Simon had been studying a bacterium pulled from Mono Lake in California. Mono Lake is a harsh, salty, alkaline place, and it's loaded with arsenic, which is a poison. Arsenic is poisonous precisely because it looks a lot like phosphorus, chemically, so living things accidentally grab it, and it jams up their machinery. But this microbe, nicknamed GFAJ1, didn't just survive in the arsenic. According to the team, it appeared to be doing something no known life had ever done. It seemed to be building arsenic into its DNA in the place where phosphorus is supposed to go. If that were true, it would be enormous. Remember, phosphorus is one of the untouchable pillars of life. Every living thing we know uses it in its DNA backbone. The claim was that here, in a lake in California, was a creature that had swapped out one of the fundamental ingredients of life for a different element entirely. And if life on Earth could be built with a different chemistry, then the range of possible life across the universe just got a lot wider. Alien life wouldn't have to look like us at all. It could run on chemistry we'd dismissed as impossible. The paper was published in a major journal. The headlines were everywhere. A second form of life on our own planet. And then it fell apart. Other scientists went to work, as they always should. A biologist named Rosemary Redfield led a careful effort to reproduce the result. And when they looked closely, they found no arsenic built into the DNA of GFAJ1. None. What was really going on was more mundane. The microbe is extraordinarily tough. It tolerates arsenic levels that would kill almost anything, but it still needs phosphorus, just like everything else, and it was cleverly scavenging tiny traces of it. It wasn't a new form of life. It was a very good survivor, misread. The correction came in 2012. And then, in a remarkable epilogue, the journal Science formally retracted the original paper in 2025, 15 years later, concluding the experiments didn't support the claim. So why put a debunked result on a list about hints of alien life? Because this is the most human item here. It shows you exactly how much we ache for the answer to be yes. We heard maybe, and half the world read it as definitely. And it's a warning that echoes across this entire video. Every one of these discoveries has to survive people trying their hardest to prove it wrong. That's not the enemy of the search. That's the whole engine of it. Number 3. The Red Rain of Kerala. In the summer of 2001, in the southern Indian state of Kerala, it started to rain blood. Not literally blood, but close enough to frighten people. From July into September, downpours of red-colored rain fell, on and off across the region. It stained clothes pink. It fell hard enough and often enough that people genuinely didn't know what was happening to their sky. When scientists collected the water and looked at it under a microscope, they found it was full of red particles. Tiny, round, red cells. Each milliliter of that rainwater held something like 9 million of them. Across the whole event, people estimated that tens of thousands of kilograms of these red particles fell. The official investigation reached a fairly calm conclusion. The red particles were spores from a local alga called Trentipolia. It's a common organism. It grows on tree bark and walls all over Kerala. And despite being an alga, it's a vivid orange-red color. A big bloom of it, spores lofted into the air and washed down by the monsoon, would tint the rain red. Case closed, more or less. Except one scientist wasn't satisfied. A physicist named Godfrey Lewis at a local university studied those red cells and became convinced they were something far stranger. He and a colleague wrote a paper with an extraordinary title, arguing that the red rain was explained by cometary panspermia. Their idea was that a small comet or meteor had broken up in the atmosphere and seeded the sky with biological cells, and the rain had simply washed those alien cells down to the ground. And then his claims got stranger still. Louis argued that these red cells could reproduce, splitting and multiplying, at temperatures as high as 300 degrees Celsius. 300 degrees. That's far hotter than anything known life can reproduce at. He also claimed, at times, that the cells seemed to lack DNA altogether. A living thing that thrives at temperatures that would cook any earthly cell and carries no genetic material we recognize. If any of that were true, it would be one of the most important discoveries in the history of biology. But here's the honest reckoning. Those extraordinary claims were never verified in peer-reviewed science. Follow-up work found the cells to be terrestrial, and other researchers reported recovering DNA from them, which fits the boring algae explanation perfectly. The consensus is that the red rain of Kerala was a natural, earthly event. Weird, beautiful, memorable, but homegrown. And yet, the story refuses to die. Because there's something about blood-red rain falling from the sky, and a lone physicist insisting the cells inside came from a comet that lodges in the mind and won't leave. It's a reminder that not every strange signal is a message from the cosmos. Sometimes the sky is just full of algae. But the fact that we can't quite let it go tells you something about us, and about how thin the line feels, in our imagination, between a monsoon and a message. Number 2, the Allan Hills Meteorite. In 1984, a team hunting for meteorites on the ice fields of Antarctica, in a region called the Allan Hills, picked up a greenish-gray rock about the size of a potato. They labeled it, bagged it, and filed it away. It sat in a collection for years before anyone realized what it was. This rock had come from Mars, blasted off the surface of another planet by an ancient impact. It had drifted through space for millions of years before falling to Earth and landing on the Antarctic ice. The rock got a name, ALH 84001, and it's about 4 billion years old, a piece of the ancient Martian crust, from a time when Mars was warmer and wetter, when it had rivers and lakes. In 1996, a team of NASA scientists, led by a researcher named David McKay, published a paper that stopped the world. Inside that Martian rock, they had found 4 things that, taken together, they argued might be the traces of ancient life. There were tiny tube-shaped and worm-like structures that looked, under the microscope, like fossilized microbes. There were carbonate globules. There were organic molecules. And there were tiny crystals of a mineral called magnetite, arranged in chains. That magnetite was the sharpest clue of all. Because on Earth, there are bacteria that build chains of magnetite crystals inside their bodies, using them like a compass to navigate. And the crystals in this Martian rock looked remarkably like the ones those bacteria make. Crystals that, at the time, scientists thought couldn't easily form any other way. The announcement was so significant that the President of the United States, Bill Clinton, walked out and addressed the nation about it. He said, "If this discovery is confirmed, it will surely be one of the most stunning insights into our universe that science has ever uncovered. A sitting president telling the world we may have found evidence of life on Mars, sitting inside a rock in a lab." And then, the way it always goes, the scientific community went to work pulling it apart. And one by one, each of the 4 lines of evidence was challenged. The worm-like structures, critics argued, were probably too small to be actual cells. The organic molecules could have come from contamination on Earth. And the magnetite, that beautiful clue, the magnetite crystals, could, it turned out, be produced without any life at all. Shockwaves and heating, the kind a rock experiences when it's blasted off a planet, could forge similar crystals through pure physics. Today, the consensus is that ALH 84001 does not prove life on Mars. Most scientists think every one of those 4 signs can be explained without biology. But, and this is the thing, it was never fully, cleanly disproven either. A minority of researchers still defend it. The debate has run for decades, and it never quite ends. The rock still sits there, with its worm-shaped shadows and its tiny magnetic crystals, refusing to give a final answer. For one afternoon in 1996, though, a president stood up and told the world we might not be alone. And the evidence was a potato-sized rock from Mars, resting on a lab bench that had traveled across the solar system to make us wonder. Number 1. The Viking Result. Everything on this list has been a hint, a gas that might mean something, ingredients that might come together, a rock that might hold a fossil, maybes, all the way down. But there is one experiment, run half a century ago, that didn't give us a maybe. It gave us a yes. And then we decided not to believe it. In 1976, NASA landed 2 spacecraft on the surface of Mars, the Viking landers. They were the first machines to operate on the Martian surface, and they carried a small suite of experiments designed to answer one question directly. Is there life in the soil? Not ancient life, not fossils, living things, right now, in the dirt. One of those experiments was called the Labeled Release Experiment, and the mind behind it was a scientist named Gilbert Levin. The idea was simple and clever. The lander would scoop up some Martian soil and drip a nutrient broth onto it, a little cocktail of water and food, laced with radioactive carbon atoms so it could be tracked. The logic went like this. If there's anything alive in that soil, anything that eats, it will consume the nutrients and breathe out gas. And that gas will carry the radioactive carbon with it. So the lander just had to sit and sniff for radioactive gas rising off the soil. Metabolism, the signature of something eating and breathing. On the 30th of July, 1976, the results started coming back, and the soil responded. Radioactive gas rose off the sample, exactly as if something in the dirt was eating the food and breathing out. Then they ran the controls, the checks designed to rule out simple chemistry. They heated another sample first to sterilize it and fed it the same broth. That one stayed quiet. No gas. Which is exactly what you'd expect if the first signal came from something living that the heat had killed. Across the 2 landers, 4,000 miles apart, the experiment returned positive results, backed by control runs. By the textbook criteria written before the mission, that was a detection of life. And yet, today, most scientists don't accept it. Why? Because of one other instrument. A separate Viking experiment went looking for organic molecules in the soil, the carbon-based compounds that life is made of, and it found essentially none. And that created an impossible-seeming contradiction. How can you have living things eating and breathing, but no organic molecules in the dirt they live in. To most researchers, that meant the labeled release signal couldn't be life. It had to be some strange, unknown chemistry in the Martian soil, an aggressive oxidant that mimicked the breath of something alive. So the positive result was overruled, not by a better measurement of life, but by an absence, by something the other instrument didn't find. But here's the twist that reopened the whole case, decades later. In 2008, a much later mission discovered that Martian soil is full of chemicals called perchlorates, and perchlorates have a nasty property. When you heat them up, the way that Viking Organic Detector heated its samples, they destroy organic molecules, which means Viking might have had organics in its soil all along and cooked them to nothing before it could see them. The absence that overruled the life signal might have been an artifact of the test itself. Gilbert Levin never wavered. For the rest of his life, right up until his death in 2021, he argued that the labeled release experiment detected living microorganisms in the soil of Mars, that we found life in 1976, and then spent 50 years explaining it away. Now, to be clear, the consensus still leans against him. The oxidant explanation is real. The caution is fair. And extraordinary claims demand more than one experiment. But sit with the shape of this for a moment. We sent 2 machines to another planet. We ran the exact test we designed to detect life. It came back positive on both landers, backed by controls. And because a different instrument didn't find what we expected, we set the positive aside and called it chemistry. Maybe that was the right call. Probably it was. But there's a version of history where the answer to the oldest question we have, are we alone, arrived on a July afternoon in 1976, printed out on a strip of data from a lander on the plains of Mars. And we looked at it, and we decided we weren't ready to believe it. That's the thing about searching for life in the universe. The hardest part might not be finding the signal. It might be trusting it when it finally comes. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.